now. And we will try to continue from last time. Where we left off at the abstracting communications chapter. But first of all, is there any questions regarding the labs or the exams or the lectures, or any questions that you feel that I need to answer? Because yeah, also this week there will be only lectures on Zoom, so I don't know when it will be physically yet, but at least next week it will be through Zoom. Yeah, okay. You don't have any questions, so let's go. Let's start. So the next chapter is about link abstraction, or communication abstraction. And in this book, you can, and all algorithms that we will talk about, you can assume that there is a link between the process on which they can communicate. And you don't need to worry about for this most of the algorithms, at least, that how the topology of the network is built. So you see 4 examples underneath, and for example A, we have all the file processes have a direct link to each other. But for example, the example C, they have the ring or the token ring type of network topology. But still there is a link, a way for each process to send a message to each other. Then we can assume that all the messages that are sent, they are unique, and also that the receiver can identify whoever sent the message. Yeah. But in our distributed systems, we need to always consider that messages can be lost or corrupted or delayed, and also delivered out of order. So the most easy thing to grasp is obviously that they are lost, meaning that they simply do not arrive. But you will see later on in also in the labs that they may also be delayed, which is makes it more complicated, and they might be delivered out of order, meaning that even if the sender sent a message A and message B, and message B was after message A, it can happen that the receiver actually receives message B before he receives message A. And this can, this complicates the algorithms, and we need to solve this. And lastly, we have that the message may be corrupted. This can be either by a hacker or malicious entity, or simply that there is a problem, a benign problem in the system somehow. Yes, so then now we'll talk about some abstractions, and we will use this abstraction and compose together to have to get more higher level abstractions. So you need to keep in mind this model that you see here, the layering model, which we talked about previously, but we will use this model when we describe the different abstractions, the different layers. So first we have the Ferro loss links, and this is the lowest level communication abstractions that we will deal with in this course. So whenever you read or you get a module description like this, it's important to see what type of events does it handle. So here we have two types. We have a request event, meaning that you use this module to send a message to a process queue, and you can use this module to also receive a message sent. So it has these four properties: the fair loss, the finite duplication, and no creation. And all of these are important to reason about. That in this algorithm, we are trying to simply have some way to send a message from a process Q to a process P in a network where there might be problems with the communication links. So the first property, fair loss, it simply states that if a correct process Q infinitely often sends a message M to a correct process Q, then Q delivers M infinitely number of times. So what this property says is that if a process Q keeps sending the same message over and over again an infinite number of times, also the process Q will deliver or receive this message an infinite number of times. And we have the finite duplication. If a process P sends a message M a finite number of times to a process Q, then M cannot be delivered an infinite number of times by Q. So this property number 2, it says that there's a upper bound of which the message can be received by a Q. So yeah, you cannot receive the message an infinite number of times if you only sent it a finite number of times. Then there's the safety property, no creation, that if some process Q delivers a message M with sender P, then message M was previously sent to Q by P. So this means that the system itself doesn't create a message from thin air. And then on top of this, we have a stubborn point-to-point links, and it has the same property number 2, no creation, and in addition we have a stubborn delivery property. If a correct process P sends a message M once, so here we are talking that we are only sending a message one time, then the process Q delivers M an infinite number of times. So with this algorithm, we can see that we only need to send our message one time, and the process Q will receive it at least once, or it will actually receive it an infinite number of times. And this algorithm, it can be implemented very easily, simply by sending the same message again and again and again. So again, we have two events: the SL send, or the send event. So whenever we use this algorithm to send a message, we trigger the lower level, which is fair loss point-to-point links. We send here, and also we add our message to a list, which is the sent line line number 3 from the bottom. So whenever we send a message, we also put this into our list of message that we have sent, and we have a timer which we can use to keep resending the same message indefinitely. So I want to see if I can somehow show my mouse. So I'll just briefly stop here. So I wonder if there's a way I can show you my mouse this way. Yes. Yeah, okay. Okay, I don't know if you can see my mouse, but kind of annoying. Yes, it's some. All right. So this is the stub-on links algorithm, and on top of this, we can build a perfect point-to-point links abstraction. So this again has the same events, send and deliver. Yeah, it works in off presenter mode. Yeah, okay, let's, I'm sure it's a setting in this keynote, but maybe I can find it there for slideshow. Allow. Yeah. Okay, let's see if there's this option. Yeah, all right, so maybe now you can see my mouse. All right, good. So send and deliver, and you have to keep in mind this is, now we have built at the lowest level was the fair loss links. Then we had the stubborn links, and now we have level number 3, perfect links. So with this module, it has the 3 properties. The property number 3 is the same as we saw before, but now we have the property 1, reliable delivery, that if a correct process P sends a message M to a correct process Q, then Q eventually delivers M. So Also here, there's many keywords that you need to whenever you see these keywords in the algorithms description, you need to trigger something that is talking about something specific. So here it says correct process. So whenever it says correct, something is correct, it means that it's not faulty. So we have two very distinct things that if a property holds only for a correct process, then it will say correct process. If we try to exchange or remove this process, if it was, for example, if a faulty process Q sends a message M to a faulty process Q, this will not hold. So if a crashed process, obviously it cannot send a message. So just keep this in mind, that it will say a correct process many times. And then we have the eventually delivers. So we will talk about this later on, but whenever you see eventually, you need to automatically think that, okay, it has something to do with time or synchrony or asynchrony, but just keep this in mind for now. Then it has the property number 2, no duplication. So remember that the lowest level fair link, this required us to send indefinitely a number of times. The stubborn link, it made it so that we can send only one time. And now with the perfect links, it allows us also just to receive one time. So you can use this, that you will you will send, the sender will send one time, and then the receiver will just get the message one time. So oftentimes, yeah, we can just first see the algorithm. It's very short. So keep in mind this uses. So whenever you see uses, this is like imports in programming, that you're importing or using a different algorithm. So here the perfect link, point-to-point links, it's using the stubborn point-to-point links abstraction. So it has the send event, and really the send event, it doesn't do anything here. It just, well, it just relays to the level underneath. But whenever a message is received, then we check here in our delivered set that we didn't already receive this message. So here we can see that it will only deliver one time. So once it's delivered, it will add this to the set and not deliver again. So this is typically implemented in lower levels in your machine. So typically this is in like standard transport level protocols such as UDP, I mean TCP. Then you will have a similar things such as this. But I don't know, are people awake? Can anyone tell me here if they see any problems with this algorithm? Why will it not? Why can you not implement this in a system so easily? or line by line. Is there anyone that see a problem here? So, well, the problem in this algorithm, or why it's not straightforward to implement like this, this is because this line delivered is now you are appending something to the delivered set. So if we try to implement this in code directly, we would soon run into problems that our memory would be filled. That if you like the slice or the array is growing forever. So this is a problem with this algorithm. So this is typically solved using what's it called, like a message number, or you attach like a identification increasing number to the message. So we will see this later on. Then we have the same thing, pretty much, called logit perfect links. So this algorithm, it's in the crash recover model. So if we allow a process to crash and later recover, we need some way to guarantee this property number 2, no duplication. So if a process crashes, it should be and then recovers later on, it should still provide this property. So what we can do is that simply when we receive a message, we can write it to the log, to the hard drive, for example, and then if we crash and afterwards come back, we can just read from the hard drive. So that is in essence, or they call it stable storage, what this algorithm does. So it has one new event, the recovery event, which you can see it's retrieving the delivered set, meaning that it's retrieving it from the hard drive, stable storage, and also in the deliver event, it's storing the message to the stable storage. Then we have authenticated perfect links, which is trying to provide the same property in a Byzantine fault-tolerant environment. So remember, in the crash arbitrary model, or arbitrary faults. So remember, in this failure model, a process can deviate from the protocol in any way. So for example, if we try to use the perfect links model here, and if a process is Byzantine faulty, it can deviate from the algorithms, meaning that it can actually skip this step, so it will deliver the message again. And similarly with the stub-on links, it can also keep resending the message indefinitely, because when it's an arbitrary fault model, it can deviate. So typically what we do when we want to handle such things in the Byzantine fault tolerant model is that we add authentication. So we add the property number 3 if some correct process Q delivers a message M with sender P and process P is correct, then M was previously sent to Q by P. So here it's providing some guarantee that this message was actually sent from Q to P. And the way that it does this is using authentication, as I mentioned. So here it's whenever the authenticated links is sending a message, it's first attaching authentication along with the message. So this can be a digital signature, or it can be a hash, or it can be a MAC. So typically in this example, it would be reasonable to use a MAC, but it would still work. The main thing is that whenever the different process receives or has a deliver event, it must be able to verify the the message. So it's verifying that the message it received was sent from P. So typically this is what you will do. So now I just wanted to test you all that if you're able to use the information so far to answer an exam question, which is very typical that you can have on the exam. And well, the question states, draw a diagram showing the protocol module composition for an application that uses perfect P2P links and operates in the failed stop model. So if we take just 2 minutes and try to answer this question. So just think about this, and we will continue in 2 minutes. All right. Anyone feeling that they want to answer this? Or is it Blanca? I would very much like to show you in the on a keyboard, on a, let's say a blackboard, but I will show you here one possible answer. Maybe you have a better answer than me. So, you know, whenever we get this type of question, which is very likely, we can start by having the top level as the application. So if we have the top level application, we are already started, you know. Then the next level is the perfect P2P links. So we need to have the perfect P2P links underneath. And remember, if we go back to the previous algorithms, we had perfect links, and it says there uses stubborn P2P links. So, all right, this tells us that we simply need to have stubborn P2P links. So we will have stubborn P2P links. And if we go to the stubborn P2P algorithm, it says here uses fair loss point-to-point links. So you need to have one more level under this. So fair loss. So now we have at least the model composition, but we need still to have the events exchanged between the modules here. So we can try to, if we, I guess, make this a little bit smaller maybe. So first, to draw the events, we can go to the P2P links algorithm, the module description. So we see here we have one request event and we have one indication event. So we can start by drawing this. So I will not draw it so beautifully. It will be something like this. I can use this mouse. Yeah. So we will have this, and we will have one deliver event. So we need to. Yeah. So we have one send event that goes from the application down to perfect P2P links, and we have one deliver event that goes the other way. So then we need to just write next to the event what is it. So this is the perfect links send. So you would do something like this, and then for the other side you would put the deliver event. So from for the stub on P2P, we do the same thing. We go to the module description. We see, okay, it has a send request event and then a deliver indication event. So all we need to do is just to copy this. Yeah, let's try this. Then put the line, do the same thing for the deliver. And write the module name, which is abbreviated just to SL. And yeah, you can already guess what we will do for the fellows. So we will put everything one more time. But what's important is that we need to check what is the name of these events. Is it really send, or can it be something different? And also, what is the module name here? So this is important details that you need to go to the module description and see, okay, it's a deliver and send, but also it's abbreviated just as FLL. So on the exam, you would write like this. So if this was the question and you were able to give such an answer, then you would get full points on this question. And typically this is, it can be 5%, 10% of the exam, such an easy question. So any questions about that, or is it clear to everyone? You will not probably not receive the specific question with the perfect P2P links, but if you get such an question on the exam, you will be provided with the module description of the algorithms that is relevant, or the modules that are relevant. So you don't need to memorize, the events names and such. So, okay, question, what path makes it operate in the fail stop? There's no path in the algorithm, or let's say, yeah, there's no path in the algorithm that makes it operate in fail stop, but it's designed in the fail stop model, meaning that when this algorithm was designed, it only accounted for processes can be in either the correct state or the crash state. So these algorithms, the perfect P2P links, the stub-on P2P, and the fellows P2P, all of them are only considering that a process is either running correctly or it's crashed and it will never come back. So different algorithms such as this log perfect links, it considers the fail recovery model, and the authenticated perfect links, it considers the arbitrary false model. So this is in relation to your question, this is a very important thing that you need to consider whenever you're asked to analyze an algorithm, that what is the failure model that we are analyzing this model under. For example, if we try to analyze this model in the fail arbitrary, we could easily say that, this will never work. But we are just analyzing in the fail stop model. So, yeah. All right. That was that. Now we will go to timing assumptions, and this is also very important to reason about when we are talking about analyzing distributed algorithms, because the algorithms, they or let's say the system, the entire system must follow one of these four models or timing assumptions. That either we say that the system is synchronous, which means that there is a known upper bound on delay. So we can know that when I send a message, we know that you must receive this message within some time. For example, we could say that we know in our system that the maximum or the upper bound of delay, it can be 10 seconds or 1 minute or 1 hour. Just we know there is a upper bound. Then the opposite is the asynchronous, which tells us that there is no bound. When you send a message, it can be received in 1 second, or it can take 1 year, or it can never be received. There is no delay, no bound on delay at all. Then we have two more classes in the middle. For example, we have this eventual synchronous, and here comes the keyword eventual again. So here it means that when we start the system, we can say that we know that there is a upper bound on the delay, but we don't know how much is it. So it's kind of similar to the synchronous, just that when it's eventually synchronous, we only know that there is upper bound, but we don't know what is the upper bound. When this upper bound is reached, the system will be considered synchronous. So when we know this upper bound, when this upper bound is known, the system can be considered synchronous after that. Then we have the fourth class, fourth type, which is the most, I would say, most realistic model. Is that you have the system that in the system it is usually synchronous, meaning that usually you can say that there's upper bound on delay, but in some time periods it's behaving asynchronously. Yeah. So now I will just go a bit more into each of these classes. Well, first, what is a delay? When I say delay, it can be computational delay, that the process is very slow. It has to do a lot of calculation and it's taking a long time to finish. Or it can be on the network or for, something with the message transmission, that you're sending a message, but it takes a long time. It has to go through the network and goes around until it's finally received. So it can be a long communication delay. We have a delay, or we have a timing assumptions about physical clocks, meaning that how much deviation is your local clock from the global real-time clock. So if the real time clock is, for example, exactly 3 o'clock, and your system can be plus or minus some seconds or even minutes from this global real-time clock. Yeah, so in the asynchronous model, as I said, we are not making any assumptions about the timing at all in either processes, links, or physical clocks. And in this timing assumption model, there's many things, that is not possible to solve. If you are very interested, you can Google this FLP impossibility result, and you can see yourself why is it not possible to implement consensus in this model. You will one key point is that when it's asynchronous, it's not so easy to know if a process is crashed or if there's just a long delay. We will go more into the failure detectors, but this is one key point. So what you typically do or must do in the asynchronous model is that you must use logical clocks, meaning that you have some counter that you attach with your message. For example, that you give or every time you send a message, you attach whatever number is in your counter, and afterwards you increment it, and the next message will be will have one higher, and so on. When we have logical clocks, we can capture causality, and causality means happens before, something was before the other. So in this example, we have well, in the A part, we have the same process is doing both events, and obviously the same process P, it can know which came before the other. If a process P is sending to Q, then you can attach the counter that P can attach the counter to the message. And in example C, over here, so when P does event 1, it attach some number, and this number is relayed to process R here. So by this you can deduct that E process or event 1 must be before event 2 when well, this line here says event 1 is before if event 1 is before event 2, this implies the time on E1 must be lower than on event 2. But the important thing to notice here is that we cannot do the opposite implication. So this is also a relevant question for your exam, that you must sometimes reason about which events comes before the other one. So if this also is unclear, please ask a question. Then yeah, the next timing assumption model is the synchronous. So here we know what is the upper bound, and if we know the upper bound of time delay, you can do implement many interesting and useful services. But in reality, it turns out that it's very difficult to find any system or build a system where you can make this timing assumption. So some things you could do if you could assume a synchronous system. You could, for example, have a timed failure detection, that if a process doesn't do the action that you expect within some time bound, you can consider it crashed. Also, you can do coordination based on time. You can have synchronized clocks, and also derive worst case performance for any algorithm, because you know the upper bound. So this is sort of a dream scenario, that you would have this. So in the real world, most often we will have a partial synchronous assumption, partial synchronous system, meaning that the system is usually it's behaving synchronously, and then there is some time periods where it's asynchronous. So we can see here that well, this tries to illustrate the model, that your system is working fine, and then suddenly it's behaving asynchronously. So it can be, for example, that part of the network was broken, or something like that. Your system, it starts running a very expensive algorithm concurrently, making your different part of the system very slow. So this is what you will see usually, and also in the labs we will mainly consider this model. Yes. So in this system model, we still have the two main design principles, that we want to be always safe. Remember that we talked about safety, that you don't want your algorithm to do something bad or something wrong, and then you want to have your system as live as possible, meaning that it will try to make progress or do something. So this is a fundamental tension. Let's say that you cannot achieve these two properties at the same time always. So only you can only have one of these at all times. Yeah. So any questions about timing or timing assumptions, synchronous, asynchronous? If you really get a good grasp on these concepts, then you have a very good foundation to understand the rest of the syllabus of the curriculum in the course, because this is really the main foundations that we will have. The abstractions regarding failures, abstractions about time, and yeah. So if there's any doubt, just ask. Otherwise, we will go briefly into abstracting time. We're already sort of ahead of the lecture plan. I guess I had suspected or expected that you would have more questions on the way. But if you don't have any questions, we are breezing through everything very fast, but that's okay too. Yeah, so next chapter, abstracting time. This chapter it tries to reason about how we can how we can incorporate time in our algorithms. Because if you remember from the fair loss links and the stubborn links and so forth, they didn't have any notion of time in these algorithms. And the way this is solved in at least the algorithms in this book is that there is a separate abstraction which we call failure detectors that captures time, meaning that it tells to us if a process is faulty or correct. But the difficult thing here is that the information is not accurate always. So what this means is that if you, for example, have a let's say a synchronous system, meaning that there is an upper bound on the time delay. If a process crashes and your upper bound is, let's say, 10 seconds, then other processes in the network will not definitely know that the crash process is actually crashed before these 10 seconds has elapsed. So this is why that even though your failure detector tells to you that a process is correct or it's faulty, you cannot necessarily trust this. and you will see this in your lab 3, where you will implement a failure detector. In the example that I told you now about, that you have a 10 seconds upper bound in your synchronous system. This is more complicated if we have the partial synchronous model, that you might not receive something from different processes in the asynchronous time period. So what you can typically do in a failure detector is that you can have a notion of suspecting that you are not quite convinced that a different process is crashed, but you are suspecting it. So oftentimes you can have one round where you are suspecting, and then another round in the algorithm, let's say, that it goes to faulty. So you can have, for example, that if your upper bound is 10 seconds, that for the first 10 seconds, if it doesn't reply back, okay, you will just mark it as a suspected process. But if another 10 seconds passes and it still didn't reply to you, then you can mark it as faulty. But again, this really comes down to what is the timing model and the system assumptions that you make. And even more complicated is in the arbitrary fault process abstraction. As you remember that a faulty process, it can deviate in any way, and it can, for example, just pretend to be correct, that it can follow the algorithm, and for all the other processes in the system, it will seem that it's correct. And you can imagine this comes into play when, if you have a malicious hacker that, for example, took over your process, and he is just making the process behave correctly, only to strike when he feels comfortable. So actually, as soon as the hacker infiltrated your system, it was actually faulty, but it's not possible to detect this if the malicious entity is following the algorithm. So this is why it can be very complicated, this failure detectors. Yeah, so so there's two main there's two sort of introductionary ways that you could imagine a failure detector, and here we have a very simple failure detector, meaning that the process P is sending a ping request or message to the process Q, and the process Q is receiving a ping back. So these two processes, they can continue sending these to ping and pong forever, and as long as both of them are replying, then they can reasonably expect that the other process is not failed. So obviously this will not work in the asynchronous model, for example, because how long should you wait for? So this is the sort of algorithm where you would attach a timeout, meaning that the process P sends the ping, and then it will wait some time period afterwards. If the process Q didn't respond back after this time period, it can just or it would assume that Q is failed. And then we have the half-beat variant, which is sort of what I just explained with the timer. And this is the exact or the failure detector that you will implement in the lab number 3. So in lab number 3, you will implement a failure detector using these half-bit messages. So in the lab 3, you will have 3 or 5 processes, and all of them will send the half-bit to each other. And you will see that when a process crashes, then the different processes in the system will eventually detect that the crash process is failed. But that's for lab 3. Yeah, so I think that we will continue with failure detectors on Thursday. And we will go more into the perfect failure detector, and also the specific one that we will use is the eventual perfect failure detector. So is there any questions so far with the labs or with the synchronous system or anything? I posted a YouTube playlist for the lectures, and well, I hope I can put all the lectures to YouTube